Okay, so what I'd like to do today is talk about meteorology, and the goal of this is to get to the point where we can talk about the transport of pollutants. Basically, what I want you to think about is how pollutants are transported through the environment. And we've seen some images before. This is actually the image on the lower right is from a site called Earth Null School. And this is actually for SO2 levels in the troposphere. So you can see the variability in this. The lines actually also show the circulation patterns. So when we look at dispersion of pollutants, the dispersion is controlled predominantly by three mechanisms. The first is the general motion of, must be Monday. So the general motion. So we've got air movement. You've seen diagrams showing the pressure differentials due to basically in the weather and how that controls weather. Pressure, the changes in pressure are controlled by temperature. If you heat up the air, pressure increases. If air is cooler, pressure decreases. And air moves from high pressure to low pressure. That will have a very significant impact on how pollutants then are transported in the troposphere. Turbulent velocity fluctuations will also disperse the pollutants, and this will tend to disperse pollutants in all directions. And diffusion, simply due to concentration gradients, will result in the movement of pollutants. Now, surface winds are affected by friction. Lots of rough, think of them as rough surfaces, buildings, trees, etc. They're going to create friction, and that's going to change the wind patterns. You can see surface winds here. This is again from Earth Null School, and you can see how the wind is moving. You can see the circulation patterns, and in the video, you can actually have captured this from yesterday, and it actually shows how the wind is moving. Now, wind movements from small gusts to large air masses, and this is showing the large air masses. It's not going to show the small gusts. But all of this contributes to the transport of heat and also pollutants. So you can imagine how pollutants migrate. So you can have, in fact, there's situations where dust particles have been monitored from Africa across the Atlantic, and actually they're able to essentially fingerprint these dust particles to identify the fact that they have come all the way from across the Atlantic. Now, as you saw in that previous diagram, wind is the basic element of the circulation of the atmosphere, and it will control both the transport of heat, but also other pollutants. The wind is always named from the direction from which it blows. So a northerly wind blows from the north to the south. A westerly blows from the west to the east. We also talk about prevailing wind. Those are the direction, the predominant direction of the wind. So, for instance, when we looked at acid rain, you saw that most of the effects of acid rain were in the Northeast. So there's power plants from the Kentucky, West Virginia, Ohio are affecting the Northeast. So what do you have? You have a southwesterly. So it's blowing from the south to the north and from the west to the east. So those are the prevailing wind directions. And those are important in terms of understanding how pollutants will move how they're transported, and ultimately, how do we control and protect public health and the environment due to the effects or from the effects of these pollutants. And then we can have eddies, and eddies are much more turbulent patterns. They're a variation from the main prevailing wind direction, and these are typically caused by convection or the vertical transport of heat. So you can get these patterns of air movement, may even be in a circular pattern. And these can contribute to the movement of dust within a particular region. So the question for us is, how does all of this affect pollutant transport? Because that's, as engineers, that's what we're looking at. And we're looking at protecting public health and the environment. So you can see these photos were taken early one morning, back a few years ago, from the parking lot outside the engineering building. And you can see very different patterns of the plume from the MSU power plant. You can see this one is much more vertical, and then it's moving horizontally. It's moving, you see much less plume, what we call plume rise. You can see here this significant plume rise here. Here, there's almost no plume rise. And this is really what you're looking at, is water vapor. But that water vapor then is transported towards the east. So you've got a westerly wind. Very different weather conditions. -2 degrees Fahrenheit here on the 25th of February. A few days later, it's actually 17 degrees. Humidity, quite different. Wind speed is also quite different. You've got a calm day versus about a 10-mile-an-hour wind. So the question we need to think about is, got these very significant differences. How do they impact transport? How do they impact public health? How do they impact the environment? Now, one of the things that we need to look at is relative humidity. And you notice in that may have noticed in the previous slide, I had relative humidity mentioned there. Now, we look at the atmosphere, the concentrations of nitrogen and oxygen and all other trace gases are relatively constant. There's very little change over time and space. On the other hand, moisture content is highly variable. And typical moisture content is about 1.15 molar percent. Now, but we typically talk about relative humidity. And what relative humidity is, it is the humidity divided by the saturation humidity. So if we take the mole fraction of water, divide that by the atmospheric, or multiplied by the atmospheric pressure, and then divide by the saturation water content at the temperature, that is the relative humidity. So you can think of it as, at a particular temperature, what percentage of water that we could have in the air is actually present. So if we look at this in terms of various different temperatures, so we'll look at temperatures of 50 degrees Fahrenheit, 70 degrees Fahrenheit, and 90. In all cases, we have a relative humidity of 50%. The partial pressure of water at the temperature given, so at 50 degrees Fahrenheit, is 92.2 torr. It is 233 torr, and it's 525 torr. Just 760 torr is equal to 1 atmosphere. So then the water content is 0.5 times 92.2, so it's 46.1. This is actually in torr. So this is the pressure of water. We can, PV equals nRT, we could relate that to number of moles, volume, etc. It is 116.5 and is 265.5 torr. So you can see, as the temperature increases, the amount of water that's present in the same volume of air increases. Now, we also talk about dew point. We'll come back to this slide in a second.
As the temperature inside the jar approaches the dew point, the air is approaching saturation and the relative humidity of the air increases. When the air temperature reaches the dew point, the air is saturated and the relative humidity is 100%. As the temperature moves away from the dew point, the relative humidity lowers as the air moves farther away from being saturated.
So looking back here, okay, so the dew point is the temperature at which water will begin to condense, so where dew forms. So it's a temperature to which air must be cooled at a constant pressure and water content to reach saturation. So the dew point at 50 degrees is 32 degrees Fahrenheit. It is 51 degrees Fahrenheit and is 69 degrees Fahrenheit. Now, some of you may recognize when you're exercising, you're often told, if you look at the weather report, it will give you a dew point, and it will tell you whether or not that condition is that condition uncomfortable. So basically, at a dew point greater than 67%, conditions are uncomfortable. On the other hand, 50% humidity at 70 degrees Fahrenheit is it's going to be quite comfortable to go exercise in. 50% at 50 degrees, it's very comfortable. In fact, if it's greater than 72 degrees Fahrenheit, then it's extremely humid. And it's even recommended you don't exercise in those conditions. And that's because at that point, condensate water condenses. So it's extremely, it's humid situation. You can see this figure here, again from Earth School, showing the relative humidity. And you can see that yesterday, it was much more humid in the northern polar regions, extremely dry in Africa. And you can see how, for instance, various changes. And it's kind of cool. If you go on this website, you can actually monitor a whole suite of conditions across the earth. Now, we're still not kind of moving towards what does all this mean, okay? Recognizing that the basic equation of fluid statics is that change in pressure as a function of depth or altitude is really what we'll be looking at, is equal to the negative density times gravitational acceleration. Density is just mass over volume, which we then can relate to the number of moles times the molar mass divided by the volume, which then we can use the ideal gas law to determine an equation where we have density as a function of molar mass, pressure, the ideal gas constant, and gravitational acceleration. So our basic equation for fluid statics can now be represented in this form here. What we will be looking at in looking at stability is both the change in pressure as a function of distance, but also the change in temperature. And notice, you look at pressure and temperature, they're inversely related. And as pressure decreases, we'll see this effect on temperature. Now, the other thing to think about is the relationship between air density and temperature and humidity. You saw the change in relative humidity on a global scale. You saw that both temperature and relative humidity varied in the situation where we looked at two different plumes. So how does air density, or how is air density affected by temperature and humidity? And what we see, if we're looking at the change in density as a function of temperature, it's roughly 3.4 times 10 to the minus 3 times the inverse temperature. This is inverse C. And on the other hand, it is about 8.7 times 10 to the minus 5. So it's about 2 orders of magnitude greater. So the effect of temperature is about 2 orders of magnitude greater than the effect of relative humidity. So basically, a 40% increase in relative humidity has about the same effect as a 1 degree C increase in temperature on density. Okay. So the wind patterns that you saw in those olographic wind patterns, those are controlled predominantly by temperature, not by relative humidity. So that's the important thing, okay? That the wind patterns, transport of pollutants, will be primarily controlled by temperature, not by relative humidity. Now, when we look at describing what we will refer to as stability and instability, we will use this concept of air density, and we'll also use the concept of adiabatic conditions. We'll think about this in terms of a balloon. Okay, so we think about a balloon rising. Okay, so we've got this balloon that's rising. As the balloon rises, what happens to the pressure surrounding it? As this balloon rises, what's happening to the pressure around outside of the balloon?
It decreases.
It decreases. So if the pressure outside the balloon decreases, what happens to the size of the balloon? It's going to expand. Okay. So that balloon rises, pressure outside of the balloon decreases, so P decreases. The volume of my balloon increases. As the volume of the balloon increases, what happens to the temperature inside my balloon? So volume increases, what happens to the temperature? Think about that basic equation that we wrote very early on in the semester. So if the volume increases, temperature decreases. Now, what we are going to assume is that as this temperature, as this balloon expands, it's going to do work on its surroundings. But because it's an accordion balloon, we're going to assume that the balloon requires no work to stretch, which means that there's no heat exchanged between the air parcel and the rest of the atmosphere. That's an adiabatic process. We are also going to assume that this process is reversible. So that means now, let's change colors. If the balloon falls down towards Earth, what's going to happen to the volume? So we bring that balloon back down to Earth. Actually, what happens first to the pressure outside the balloon? The balloon's descending down towards Earth. What happens to the pressure outside the balloon? It's going to increase. So if the pressure outside the balloon increases, what happens to the volume of the balloon? Exactly. The volume's going to decrease. And then what happens to the temperature of the balloon? It's going to increase, the exact opposite to before. Okay. So what we are going to describe, or the concept we're going to use, it's what's referred to as the adiabatic lapse rate. That is the rate at which the temperature is changing with altitude. We will assume, as I mentioned, that no heat is transferred between the balloon and its surrounding. So that's the adiabatic part of it. Now, the dry adiabatic lapse rate is this rate of change in temperature. So what we're looking at is a change in temperature with elevation. And that change of temperature is such that the air is unsaturated. So condensation doesn't occur. Under those conditions, we can assume that there is a 10-degree decrease in temperature with every kilometer increase in elevation. It's about 10. It's actually somewhere between 9.6 and 10. We'll assume it's 10. So let's think about this here. Okay. We start out with an air parcel at 30 degrees. We move up 1,000 meters or a kilometer. The temperature decreases by 10 degrees. So this is the change in temperature. So now the parcel, the volume increases, temperature decreases, and it is 20 degrees. If we let the balloon rise even further, so now we let it rise up to 2,000 meters, again, delta T is equal to minus 10 degrees C, and the temperature is 10 degrees. So it's decreased another 10 degrees. If I let it rise up to 3,000 meters, what's the new temperature? So we're going to go from 2,000 to 3,000 meters.
0 degrees.
0 degrees. And it's even bigger. Okay. Volume increases even further. So volume is increasing, temperature is decreasing. I bring it back down again. It's a reversible adiabatic process. So if I bring it from 3,000 back down to 2,000, we're back to the same volume we were before, and we're back to 10 degrees. I bring it further down, but because the outside pressure is increasing, volume decreases, temperature increases, back to 20. And when we go back down to ground level, we're back to the 30 degrees C. Okay. So it's reversible and adiabatic. This is the dry adiabatic lapse rate that we've used to describe the temperature, and we could also use it to describe the volume using the ideal gas law. Now, what happens when we have moisture? Well, when we have moisture, when water evaporates, heat is absorbed. When water condenses, heat is released. Now remember, it's adiabatic. So if it's adiabatic, what does that mean in terms of heat? So if we have an adiabatic process, what does that mean in terms of heat? Okay, essentially, so what it means, the adiabatic part of it means that no heat is transferred. Okay, so if no heat is transferred, so water is condensing, if we have moisture and the temperature is cooling, then you're more likely to have condensation. But if heat is released, what do you think that means? Okay, if we have let's start with that balloon here. Okay, we're going to go up. We said that if it was dry, this balloon would be at 20 degrees C. So this is a situation dry. This is a situation where we have moisture. The balloon rises 1,000 meters. The temperature inside that balloon, is that going to be 20 degrees C, greater than 20 degrees C, or less than 20 degrees C? Let's assume, we're going to assume that water is condensing. So is this temperature in this balloon here? Okay, so we've got less than 20, greater than 20, another greater than 20. It's going to be greater than 20. It's going to be greater than 20. Why? Because heat is released. There's no transfer of heat. If heat is released, then the temperature is greater than what we would have predicted if there were no moisture. So the air is warmed. We can then talk about a moist adiabatic lapse rate. And this, we said, was about 10 degrees C per kilometer. This moist adiabatic lapse rate is about 6.5 degrees per kilometer. So that difference is because of the release of heat when water condenses. So it's because of this latent heat of condensation. Now, it's more complicated with the moist adiabatic lapse rate because that will depend both on temperature and moisture. But for what we do in this class, we can assume it's 6.5 degrees C per kilometer. We will use this for the moist adiabatic lapse rate. It's new concepts.
So as the balloon rises, the temperature inside the balloon decreases, and also of the atmosphere it decreases.
Don't worry about the atmosphere yet.
Okay.
Just worry about the balloon. We'll worry about the atmosphere next.
Okay. So what causes it to ascend? The decrease in temperature?
Right now, it's hooked onto a helicopter, and the helicopter is bringing it up. Just think of it that way.
Okay. Okay.
Okay.
Gotcha.
So we will ultimately compare the two, and then we'll look at whether it would ascend or not. But in terms of this adiabatic, think of it with the image here that the balloon's hooked to a helicopter, and we're causing it to rise. So what you see here is the dry adiabatic lapse rate. So here's our balloon. So it's our balloon hooked onto the helicopter, and we're carrying that balloon up. So think of it that way. So we start here at 30 degrees at ground level. As we're at 20 degrees. So here's our dry adiabatic lapse rate. So we're 20 degrees at 1,000. We're at 10 degrees at 2,000 meters and 0 degrees at 3,000. So that's our dry adiabatic lapse rate. The line that you see, and I'll highlight this. So that line there is the environmental lapse rate. So if we were to, using our helicopter, we've got a temperature probe on the outside of that helicopter to measure the temperature of the atmosphere. This is the data we would obtain. So it's 30 degrees. At 0, we carry that balloon up to 1,000. We measure the temperature, and it's, 28 degrees. Maybe it's 27 degrees at 1,000. And let's say it's 26 degrees at 3,000. So this is what we actually measure. That's the environmental lapse rate. Now, what we're doing is we're going to then compare our balloon to the environmental lapse rate. And that's how we will determine stability. And we'll go through a whole series of conditions this way. Okay? So think about your dry adiabatic lapse rate as the hypothetical situation. Here's your balloon. Your balloon is being carried up in the atmosphere, okay, with elevation on the helicopter. The environmental lapse rate is what you actually measure. And we'll always be comparing those two, or if we have moisture, then we'll use the moist adiabatic lapse rate. So that gets to the point where we have to ask the question of, do we use the dry or the moist adiabatic lapse rate? And that's going to depend on whether or not clouds are formed. So we talked about dew point, the temperature at which air is saturated, and any further cooling results in the formation of liquid cloud droplets. So we've got condensation that's going to occur at the dew point. Latent heat is given off as a result of condensation, and we showed how the moist adiabatic lapse rate was less than the dry adiabatic lapse rate. We can also then determine where clouds will form, because remember, we need to know which one to use. Clouds will form when the parcel temperature is equal to the dew point temperature. So that parcel temperature is your air temperature at ground level minus the dry adiabatic lapse rate times the height, and we'll set that equal to the dew point at ground level minus the rate and change in the dew point temperature, that is not the moist adiabatic lapse rate. That's the rate of change in the dew point temperature. You need to be given that. And where you would get that is from the atmospheric conditions times the height, okay, because it's at where the height is equal. So we can solve a problem like this, where we have the situation. So we have a ground level temperature of 27 degrees. The dew point at ground level is 11 degrees. So this is our dew point. Okay, this is our ground temp. The dry adiabatic lapse rate, you're told, is minus 10 degrees C per kilometer. And you're told that the rate of change in the dew point temperature is minus 2.5 degrees C per kilometer. And you can get this data from a variety of meteorological sites. So usually typically related to airplane transport. So this will set this 27 minus 10 times that height is equal to 11 minus 2.5 times h. So it's the height where the parcel temperature is equal to the dew point temperature. So that height. And this, if we solve it, is equal to 2.13 kilometers, or so under these conditions here, we'll use the dry, so here's ground level, we'll use the dry adiabatic lapse rate up to 2.13 kilometers. After that, we'll use the moist adiabatic lapse rate. That's where clouds form.
Wait, did you say we use two different rates there?
We're going to use two different rates. Here's where the clouds form. Okay, so the clouds are going to will form at 2.13 kilometers. So when we're looking at that balloon or part rising or lowering or descending, we'll use the dry adiabatic lapse rate to 2.13 kilometers. We'll use the moist adiabatic lapse rate because we have condensation occurring at altitudes greater than 2.13 kilometers. Yes, it does. Okay, for a little fun to end this, before we continue, we'll finish this next on Wednesday. See what we can do in the last couple minutes. So this is we've seen clouds. Question is, how high are those clouds? When would they really form? Okay, in the situation here that we just had, we had low clouds. They formed at about 2,000 meters. What kind of low clouds form at about 2,000 meters? Anybody want to guess? All right. Any others? How about some high ones? Okay, well, cumulus. Okay, cirrus, so those low or high. How about contrails? Where are those? All right, how about cirrocumulus? Cirrocumulus, we've got high. Let's see. All right. How about altocumulus? Alto, you guys are good. Where do you want to put altostratus? Should put that in the middle? Got middle on there, so we're going to put that in the middle. All right, we got two left. Where should we put stratus cumulus? We said middle? All right, we'll put them in the, uh-oh, not the middle. We got low? It's low. Okay, cirrostratus. All right, nice job. I just thought we'd do this at the end. So next time you look at the clouds, okay, think about it. Think about it in terms of transport. So great job. We will continue on looking at transport, looking at stability of atmospheric conditions on Wednesday, and we'll do a few more problems on that, but I thought this would be a fun way to just end the lecture. So I will see you on Wednesday.